Hi, in this video we're going to start the talk about integral approximations using the trapezoidal rule. Now, when I say integral approximations, I do mean that we're talking about definite integrals. So we're looking at the integral from a to b of some function of x dx. So the standard way we would do this using Riemann sums is, say we had a function f. And we were integrating from, say, a here to b here. What we would normally do is we would divide the interval evenly. Let's just pretend that's an even division. And we would say a is maybe x naught, we'd have x1, x2, and so on to xn minus 1, and b is going to be xn. And then we would either take the left or right-hand side. I'm going to use the right-hand side for this demonstration. And we would see what the value of the sum of these rectangle areas are. So we know that the integral of f of x dx from a to b is approximately the sum of the areas of the rectangles, right? And we know that that is the sum of delta x sub I times f of x sub I, right? So where delta x sub I is going to be b minus a over n, where n is the number of divisions, and b minus a is the length of the interval. And x sub I is going to be one of these endpoints. Or we can do it in the middle, or we could do it on the left side. So it depends on how you want to use your Riemann sum. But we know that the limit, or that's approximately equal to these, we know that if we take the limit as n goes to infinity, or as we decrease these to almost nothing, the integral from a to b of f of x dx is actually equal to the limit as n approaches infinity of this sum as I goes from 1 to n of f of x sub I delta x sub I. So this is our Riemann sum. Now we notice that if we don't divide it into really, really small intervals, what we have is not a very good approximation. So what we're going to do in the next several videos is look at 3 separate ways that we can approximate it slightly better. We're going to be looking at the midpoint rule, which I hinted at when we were talking about Riemann sums. We're going to be looking at the trapezoidal rule in this video, and we're going to be looking at Simpson's rule, which approximates things using parabolas. So let's look at the midpoint rule. So the midpoint rule is the closest possible one to the Riemann sum. But instead of looking at the endpoints, like the Riemann sum does, so the Riemann sum looks at endpoints, what we're going to be looking at creatively, the midpoint rule looks at the midpoints of each interval. So we're doing the same exact procedure as the Riemann sum, except we're looking at the midpoints instead of the interval, instead of the endpoints of the interval themselves. So let's take the interval 1 to 2, and let's divide it into 4 even 1, 2, 3, 4 almost even intervals. I'm not the best at drawing, but it's the numbers that matter in calculus. So let's find out what delta x is and allocate each of these points appropriately. So I think that's a little better. So delta x is the same as it was with the Riemann sum, b minus a over n. This will be 2 minus 1 over n, which is 2 minus 1 over the number of intervals we're dividing it into, 4, which is 1/4. So our endpoints for each interval are going to be 1, which is x0. x1 is going to be 1 plus a fourth. x2 is going to be 5/4 plus a fourth, so 6/4. x3 is going to be 7/4, and x4, which is our right endpoint, should be 2, and it is. So let's just write it as 8/4, and let's rewrite x0 as 4/4. Now what we want, so let's go back to, let's actually graph e to the negative x squared. So you might notice that it looks kind of like a normal distribution if you've taken statistics, and that's because it is not quite that, but it is a non-normalized version of your normal Gaussian curve. So let's look at 1 here, maybe a 2 here, and we'll divide it almost evenly into 4 distinct parts. So we're looking for the area between these 2 points. Now if we were doing the Riemann sum, we would pick the right endpoint and make our rectangles, or the left endpoint and make our rectangles. But what we're going to do here is we're going to pick a point in the middle of each of these intervals, and that function value is going to serve as the height of our rectangles. So when we approximate it, we're actually getting this red area here. So to find out what that is, let's go ahead and find the midpoints. So our midpoints. And on the interval from 1 to 5/4, what we're going to have is 9/8, because that is 4/4, and we're going to subtract it from 5/4, and we're going to divide that by 2. So we have 1/4 divided by 2, which is 1/8. And since we divided each interval evenly up, the midpoint is always going to be the same distance from the left endpoint. So this is the distance from the left endpoint. So that tells us the distance between 5/4 and 6/4 is 11/8, or 1/8 to the right of 5/4. The midpoint of 6/4 and 7/4 is 13/8, and the distance between 7/4 and 2 is 15/8. Now what we're going to do is we're going to make a small chart here where we have 9/8, 11/8, 13/8, and 15/8, all of our endpoints. And we're going to evaluate f of x at each of these points. So we're just going to plug 9/8, 11/8, 13/8, and 15/8 into x for e to the negative x squared. And we're just going to plug in their approximate values. And then at the end, we're going to add them up, and we're going to see what we get. So let's go ahead and plug those into a calculator. So quickly plugging these in, we get 0.28 approximately to the nearest hundredths. We get 0.15, 0.73, and 0.30. And when we add all of these up, we get 0.53. Now, our midpoint formula for approximation is that the integral from a to b of f of x dx is approximately the sum, as I ranges from 1 to n, of f of x sub I delta x. But delta x is just a number. So by factoring, we can pull it out. And I can just write this as delta x times the sum of f of x sub I from 1 to n. So for us, the integral from 1 to 2 of e to the negative x squared dx is approximately equal to our delta x times the sum of e to the negative x squared, or negative x sub I squared, as I ranges from 1 to 4. And each of these x sub i's is our midpoint on the interval, on the intervals that we specified. And we already calculated it, so it's 1/4 times 0.53. And 1/4 times 0.53 is approximately 0.13. Okay. And if you were to write it out, it'd be 3,521,567. Okay. Now let's compare our approximation to the actual value. Now our actual value is 0.135257. So let's do a small percent error approximation. So we know it's the actual, so 5257, minus the estimate, so 133,522, just to keep consistent with the number of decimal places, over the actual, 0.135257, all times 100. And doing our approximation, we get a 0.03% error. And that's not too bad for just a simple modification of the Riemann sum. If you want to check the Riemann sum approximation using n equals 4, you're more than welcome to. But for us, so the next one we're going to be looking at, again, is the trapezoidal rule. The trapezoidal rule approximates an integral using, creatively, trapezoids. And it tends to be better than Riemann sums and midpoints, even though it's not as nice of a formula to deal with. So let's go ahead and look at the same integral that we did before, and the same number of intervals that we did before, e to the negative x squared from 1 to 2 with 4 intervals. So we know what our intervals are now. So if this is 1, this is 2, we pretend it's a straight line. We have 5/4 because delta x is 1/4. We have 6/4 or 2/3, we have 7/4, and we have 8/4, which is 2. So looking at our graph again, we'll pick 1, we'll pick 2, and we'll subdivide it. And now instead of looking at midpoints, what we're going to do is we're going to take these two endpoints, connect it with a straight line, and look at this trapezoid. And then we're going to do the same thing with each of those intervals to get a fairly better approximation of the area under this curve. So let's start by recalling what the area of a trapezoid is. So the area of a trapezoid is going to be base times height 1 plus height 2 over 2. So these trapezoids do share points. So if we're looking at, say, a generic function, say f of x from a to b, what we're going to have is we're going to have base, which our base is always going to be delta x, times f of x1 plus f of x2 over 2. And then we're going to have f of x2 plus f of x3 over 2, and so on, plus f of xn minus 2 plus f of xn minus 1 over 2 plus f of xn minus 1 plus f of xn over 2. And all of these share a common point. So we have f of x2, f of x3 is going to be shared with the next one, f of xn minus 2 is shared with the previous one, and f of xn minus 1 is shared. So the only ones that are alone are the first one and the last one. So that tells us that our approximation is going to be delta x over 2 times f of x1 plus 2 f of x2 plus 2 f of x3, and so on. And at the end, it's 2f of xn minus 1 plus f of xn. So what does that mean in our case? Well, for us, remember, we're integrating e to the negative x squared from 1 to 2 with 4 intervals, so n is 4. So let's figure out what our delta x is, what our f of x sub i's are, and in order to do that, we're going to have to find out what our x sub i's are. So we know what delta x is. It's 2 minus 1 over 4. And that is 1/4. So we know what x1 is. x1 is going to be 1. x2 is going to be 5/4. x3 is going to be 6/4. x4 is going to be 7/4. And our last point, which is our end point, is going to be 2. Now notice that there's one more point because we have to take into account the endpoints here. So now let's look at what f of x1 is, f of x2, f of x3, f of x4, so looking at the approximations of these, we get 0.367. We get 0.209, 0.105, 0.468, and 0.018. And now we have to multiply this by 2, this by 2, and this by 2. And when we do that, we get 0.419, 0.210, 0.09. So this is actually 0.0468. So we get 0.94. And let's just rewrite this, our two endpoints. So now we're going to add all those up, and when we do, we get 1.1098. So we have the integral of e to the negative x squared from 1 to 2 is approximately delta x over 2 times the sum that we have here. Delta x over 2 is 1/4 over 2, or just simply 1/8, times 1.1098. And this is 0.1387. Okay. Now let's do our percent error for this. So recall what the original value is. It's 0.135257, and we're going to subtract what I got from my calculation, 0.138719, or 20. And we're going to divide this all by 0.135257. And doing that calculation, we end up with negative 2.56% error. Not as good as our midpoint rule, but it's still pretty good. So this negative isn't normally calculating our percent error. That just tells us that it's less than the. I hope this helped you understand some approximations. In the next video, we will be talking solely about Simpson's rule.